All right, let's look at signed numbers. And by signed, it means it has a sign, either positive or negative. The value can be either one. If I came to you and said, "What is this number?" you would say, well, that's an 8, 4, 2, and a 1. So 8 plus 1. The result of that in decimal is 9. In binary, it's 1, 0, 0, 1. But what if I wanted to do, I don't know, negative 3? Okay, how would I represent a negative 3? Every form I've shown you of interpreting these numbers has always been positive. Okay, we start out, here's 0, and here's 1, and here's 2, and here's 3, and so on and so forth, all the way until all of the bits are turned on. And that's 15 decimal, that's 15. F in hex, and in binary it's 111, but it's still a positive value. Right? We don't have any negativity to it. So how, using the current schemes that we've seen with the bits, how could we represent negative numbers? Pause the video, think about that one, and then come back. The initial response, let me just get rid of these. Let's deal with 3 bits, okay? 4 bits is taking a long time to write. Let's do 3. Okay, your initial thought may be, you know what, let's sacrifice this bit, and if it's a 0, then it's positive, and if it's a 1, it'll be negative. Alright, so 1, 0, 1 is no longer 4, 2, 1 making a 6. Instead, this is our negative bit here, so this is the sign bit, and thus the result of this would be negative 1. Alright, well, that seems kind of reasonable. So far, so good. What is this value then? Well, it is negative 2 plus 1 is a 3. Negative 3. Alright, well, so far, so good. But what do we lose by this? We actually lose something by it. Let's first list out all of the bits we can get with three values here. So we'll put 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Alright, let's put the equivalent signed decimal value out here to the right. I'll just say decimal, like so. Alright, this is going to be a 0. Fair enough. And then this is a 1, and this is a 2, and this is a 3. So no surprises there. Very good. But now down here we have negative 0, which might make you wonder, we already have a 0. Why do we need a negative 0? Negative 1, negative 2, and negative 3. Okay, now let's do their unsigned, meaning only positive values here. So this is a 0, 1, 2, 3, 4, 5. I'm trying to keep these lined up as best as possible. 6, 7. All right, how many values do we have with this range? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. Very good. How many do we have with this range? Well, 1, 2, 3, 4. This can't be 5 because 0 is equal to 0. So this one's 5, 6, 7. All right, on the right-hand side, we have 8 distinct values. On the left-hand side, we get 7. So we lose one value. Well, okay, maybe we can sacrifice one value. That's fine. But now we have this ambiguity. We have this 0 with positive 0. Well, not even positive video, it's just 0. And then this negative 0. What does that mean to be in debt? $0, negative $0. Whatever. And then another issue that comes up with that is when we add and subtract numbers. I mean, say I have, I don't know, this 2 here. Let's put it out here. 0, 1, 0. And I want to subtract the negative 1. So let's do that. And then what does this mean exactly to subtract? 0 minus 1. Well, now I got to borrow from this guy and so on and so forth. We could do that. But what we actually do is a different notation called 2's complement, which allows us to simply add when we want to subtract. Okay, that's long story short. Well, we'll get into that very quickly. Look at this. First of all, 2's complement. All right, this is, I'm going to put the signed bad decimal way of doing things. Okay, this is the decimal column. All right, and this is the binary. I'll put binary right there. I should have labeled these originally. And then right here, let's do the decimal values again. All right, signed decimal values again. This is unsigned. I'll put unsigned right here. Unsigned meaning only positive values. And then these signed values, these signed decimals. We made an attempt doing it here, but it didn't go out very well because, yeah, anyway. What we really do to interpret negative values in 2's complement is the positive values are all the same. So this 0 is still a 0, and the 1's still a 1, the 2's still a 2. No big deal. Alright, but then these values here that have these bits set right here, the leftmost bit, yes, it indicates negative again, but we interpret the values a little differently. So the bottom one here will be -1, alright, and then this one is a -2, and then -3, and then -4. So in future videos I'm going to show you why this works, but we like it a lot. And so when I give you a 2's complement value, all you need to do to find the value of that value is flip the bits and add 1. Okay, let me just try a few examples. First of all, what is this value? Without looking down here, what is this value? What's the decimal value? Well, you can see it's not negative, so then you just interpret the rest of the bits as is, and this is a 2 in binary, so that's in decimal, it's 2. It's a positive 2. Well, let's try another one. Let's try another one. Again, don't look down here. All right, maybe I'll take this off the screen, and let me give you 1, 0, 1. What is the decimal value for this binary number? This signed binary number. Signed meaning it can be negative. Well, again, this bit is turned on, so it's negative. How do you find out what it is? Well, it's simple. You take the rest of the bits. Okay, here's the rest of the bits. You invert them all, or flip them. So a 0 becomes a 1, and a 1 becomes a 0. And then you add 1. All right, and then 0 plus 1 is, not 0. 0 plus 1 is 1. Okay, 1 plus nothing is 1. And then you just say, hey, this is a 3. All right? You can look at it as an unsigned value now, a positive value. 1, 2, this is a 2, and then the 1, and 2 plus 1 equals 3. That should be old hat by now. And so we know this is a 3, but we also know it was a negative. So the result is actually -3. Okay, this 101 equals -3. We can verify that here. 101, -3. Very good. And that's how 2's complement works. You can do this with as many bits as you have. Let's try one more bit. Let me new page. Let's say 1, 1, 0, 1. All right, now we have 4 bits, not just 3 bits. We have 4. Okay, is it negative or is it positive? Well, it's negative. And since it's negative, that means I need to take the remaining bits, flip them, and add 1. So 1 flipped, and when I flip them, we call that the 1's complement. All right, we invert all the bits. That's the 1's complement. So 1 becomes a 0, 0 becomes a 1, 1 becomes a 0, and then to get the 2's complement, this is the 1's complement. To get the 2's complement, we simply add 1. The result will be 0 plus 1 is 1. 1 plus nothing is 1. 0 plus nothing is 0. Oh, look at that. Look at that. Again, this is a 3. Okay, this is a 2 plus 1 again. I didn't really intend for that to happen, but it did. That's a 3, but I know it was negative, so again, -3. All right, 2's complement. So 1, I want to outline this a little bit. Let me list the general rules here as best I can. I'll try to make it nice and big. Okay, rule number 1. Check if leftmost bit is set. Number 2. If not, interpret value as always, meaning it's positive, what we're used to, the easy stuff. Okay, number 3. Else, flip let's do else like this. Else flip the remaining bits 1's complement, and I just went off the screen. Let's go over here. 4, or that's 5. 4. Who's doing these lectures anyway? Holy smokes. Else flip the remaining bits. 3. Let's see. Add 1. Add 1 to the flipped bits, or inverted bits. Remember, I use the word inverted as well. It's the same thing, different terminology. And then 5. Interpret the resulting value as negative. Okay, a little bit of a workout, I know, but that's all there is. And then the cool part is how this works. Okay, because we can use 2's complement values to easily do subtraction. And the way we do subtraction is by adding negative numbers. Anyway, I'll get into that in the future videos.